Hey guys, I wanted to talk to you today about something called the law of sines and the law of cosines. And obviously, we know what we have here on the screen here is just SOHCAHTOA stuff we already know, and how that applied to the unit circle. And essentially, what sine and cosine and tangent allow us to do is if I have a right triangle, which means I know there's a 90-degree angle, and I have any given angle and some side, then I can find the other sides. And obviously, we know how to find the other angle as well. So that's great, but there are lots of triangles that aren't right triangles. And that's what the law of sines and cosines are for. So I want to kind of get into what those tell us exactly. So here's the law of sines. This works for any triangle. Well, I'll kind of get into when it works exactly, but we use this for when we don't necessarily have a right triangle, although it still would work for a right triangle. And what it's saying is that if you take any side and divide its length by the sine of the angle opposite, that ratio is going to be the same no matter which side and opposite angle you choose, right? So side A divided by the sine of angle A is the same as the length of side B divided by the sine of angle B, and side C divided by the sine of angle C. And it's, again, lowercase letters always stand for side lengths, uppercase letters stand for angles. So it's a pretty straightforward, easy to use kind of situation. Let's just look at example. And actually, before I go too far with the example, I do want to mention sometimes you'll see this exact same law written upside down, and they both work just the same. Obviously, the ratios are reciprocals, but it still is true either way. I don't really know. There's no reason one's better than the other. I generally put the side on top, but it doesn't really matter. So if we look at this example I have up here, notice that we have three given pieces of information. We have two sides and one angle in this case. And in order for the law of sines to work, one of the sides that you're given has to be across from one of the angles that we're given. So we can go ahead and set up that 14 divided by the sine of 35 is equal in this case to 17 divided by the sine of whatever. There's no letter here, so whatever. You can letter it yourself. I'll call it B and C. So we know that that's 17 over the sine of B. And once you have this set up, it's super simple to solve. All we need to do is cross multiply. So we're going to get 17 times the sine of 35 has to be the exact same value as 14 times the sine of B. Obviously, if I'm trying to solve for B, then I'm going to divide both sides by 14. And when I plug this in the calculator, we get that, that the sine of B is equal to 0.6965. And obviously, or I don't know, it's been a while since we've done this actually. So if we want to go backwards to find out what the measure of this angle is, remember we have to do what's called the sine inverse, right? Because that would cancel the sine. So angle B would be equal to the sine inverse of 0.6965, which in this case would give us 44.15 degrees. And so now we know two of the angles in this triangle. And so if I tried to set this up, I don't know side C or sine or angle C, but how can we find angle C now that we have two angles? Obviously, we know that the three angles of a triangle add up to 180. So if I subtract the two that we know from 180, we find that the measure of angle C is 100.85 degrees. And now I can go ahead and set this up again, where C over sine of 100.85 is equal to, and you can choose either of these two. I prefer to use the original information That way there was no rounding and I can just be a little bit more accurate. So we know that 14 times sine of 100.85 is equal to C times sine of 35. And when I divide, I will get the measure of the length of side C. So we get 23.97. Also, I think it's important when you finish a problem like this to make sure that your answers make sense in terms of their size. So in other words, 23.97 is by far the largest of these three sides. It's bigger than 17. It's bigger than 14. Well, our longest side should be across from our largest angle. So it makes sense that 100 degrees is across from our biggest side. 14 is our smallest side and 35 is our smallest angle. So that's checking out. Let's look at one more example. So here's another triangle. This time we have two angles in one side, but the more important part is this angle 35 is across from that side 7. So law of sines does apply here, right? So we can set this up. Again, it's pretty simple. I'm sure you can pause it and do it yourself at this point. We're going to cross multiply. We get 7 times sine of 105 is equal to C times sine of 35. I'm going to divide by sine of 35 on both sides and find out what the length of C is. So I'm getting 11.79. Sometimes it'll say centimeters or feet or something like that. Again, we can find the measure of angle A by doing 180 minus the two angles. And that ends up giving me 40 degrees for angle A. And so if I want to find that, hopefully we can anticipate here my length of side A should be bigger than 7 and less than 11.79 because 40 degrees is bigger than 35 but less than 105. So I think it is good to kind of anticipate that. So again, we get 7 sine of 40 equals A. Oh, I just set this up wrong. I must mess this up. 7 is across from the 35, excuse me. So A times sine 35. Again, we're going to divide by sine 35. And when we do, I get 7.85, which fits our prediction there, which is nice. So this is pretty straightforward, but I do want to show you a couple other things, particularly when it doesn't work. So here, if you look at this example on the left, if we started to try to set this up, I would have C is across from angle 37. 8 is across from angle A. 11 is across from angle B. We don't have any pairs of information where I know both, right? Like you're going to need to be able to have no variables on the top or the bottom of at least one of these. So in this case, no matter what, when I cross multiply, it doesn't matter which of these two I choose, I'm always going to have two variables in my equation, and that's no good. Same thing's happening on this right example, right? I would have 19 over sine of x and 8 over sine of whatever letter you want to put over there, call it y or z or a or whatever. I could have 14 over sine of z, but I would have two variables in any equation, and I can't have that. You have to have given at least one pair that's opposite itself or its angle where I know both numbers. So these are examples of when you need law of cosines. So let's go ahead and look at that. So here's a look at the law of cosines. Before you get too intimidated, maybe I shouldn't have done it this way, but it's not all of these equations at once. It's any one of these. Like you can just write it in different order. So let's take this bottom one, for example. So if I wrote it in a different way, hopefully this looks a little bit familiar because a squared plus b squared equals c squared is Pythagorean theorem. This is very similar to that. The difference is, since we don't have a right angle, we need this other little part involved. Okay, so the way I remember this, and I know it doesn't matter for online learning because you're going to have this at your disposal. Even on ACT, the ACT loves to ask questions about law of sines and cosines towards the end in the 50s. And they usually give you the equation, but just in case you need it, notice that the side length that's by itself in the equation, it is the same as the angle that's in the cosine. Everything else are the other two sides. So let's stop talking and look at an example. So if I look at this triangle here on the left, notice again the angle that I have. I only have one of them, and I don't know the side that's across from it. So I already know I can't use law of sines. And so in this case, you can kind of work backwards, but the way I always try to think about it is the angle that I have, that's going to go in the cosine part of my equation, which means the side across from it is what's going to be on the other side of the equation. Okay, so I know that we don't have A, B, and C, but I wanted to do that on purpose so that you realize that the point of all this is not the letters. The letters aren't what matters. What matters is the relationship. So side Z is across from angle 131, which means Z squared is what's by itself. The other two side lengths are what goes in the equation. So 9.4 squared plus 6.5 squared minus 2 times 9.4 times 6.5 times the cosine of 131 degrees. When you're given information in this setup where one angle is between two sides, it's really simple to solve this. You're just going to plug it all in the calculator a little bit at a time. So 9.4 squared gives me 88.36. 6.5 squared is 42.25. And then 2 times 9.4 times 6.5 times the cosine of 131 gives me 23.06. And so all you're going to do is add this stuff up. And we get that Z squared is equal to 107.55, which means when I take the square root of both sides, you get 10.37. Okay, so now I have all three sides. I don't think I need to show you this, but if I asked you to then solve for like angle Y or angle X, I would go back and use law of sines now because I have 10.37 across from the sine of 131. And then you could do like 6.5 is across from the sine of angle Y and so on. So I'm not going to do that right now, but that's how you would find the missing lengths or angles. And let's look at another example where it's a slightly different order of what you're. So let's say that we have this example where we're being asked to find the measure of angle A. So again, what that means is if you kind of think of it working backwards, you're going to have cosine A here, which means on the other side of the equation, you're going to have A squared. And so we're going to have B squared plus C squared minus 2 times B times C times the cosine of A. Like that's what we're plugging into. And in this case, remember, our angle and our side are across from each other. So 8 is your A. So 8 squared equals 6 squared plus 7 squared minus 2 times 6 times 7 times the cosine of A. When you are using the law of cosines to solve for an angle, and you're going to have to work backwards, it's really, really important that you're careful about the order of operations. So let me show you what I mean. So obviously we have 64 equals 36 plus 49 minus 84 cosine A. We have to remember that this is all one term. They're all being multiplied together. So when you add together 36 and 49 and you get 85, you are not subtracting 84 and getting 1 cosine A. This 84 cosine A has to stay together. So to solve this, you're actually going to subtract 85 from both sides, which would give you negative 21 equals negative 84 cosine A is still attached over here. So if you want to move that 84, you're going to have to divide both sides by that negative 84. And that's how we're going to get cosine A by itself. And I don't know if I might have just brushed through this too quickly, but this minus sign has to stay attached to it. That's really important. So notice that when you had a negative divided by a negative, we get positive 0.25. And then if I want to try to solve for A and work backwards, we have to do inverse cosine of 0.25, which tells me that angle A ends up being 75.52 degrees. So it is possible for you to have a positive number on the left and divide by a negative. Remember that if the cosine is negative, just think about unit circle. That just means you're over here in quadrant 2. So if this angle happens to be more than 90, then this value right here could be negative. That is possible. So don't get freaked out by that. So I don't want to do a million more examples. This is the basics of it. I especially wanted to go over this because it does pop up on ACTs a lot. But let me show you one more example with the word problem, because that happens every once in a while too. The other reason I wanted to give you this word problem is because the biggest thing is that you have to be able to decide whether you should use law of sines or law of cosines. So in this case, it says that the surveyor was at one end of the lake. He started here. He walked 245 yards in this direction. He then turns 110 degrees. If he was facing this way, he turned 110 and walked 270 yards to get to the other end of the lake. So that means if he wants this length X, that 70 degrees is what's actually inside the triangle. So I want you to take a second, maybe pause it, and think about whether we should use law of sines or law of cosines here. I'm just going to keep talking because I'm assuming you paused it. So in this case, the only angle we know across from side X, we do not know that side. So we can't use law of sines unless we knew what this length was. So we're going to be using law of cosines, which means this side length that we're looking for is the one that's by itself. So I'm going to have x squared equals 270 squared plus 245 squared minus 2 times 270 times 245 times the cosine of 70 degrees. And from here, we're just plugging in and find out what we get. So when I plugged all that in, I got 87,675.74. So if you didn't do that, be careful with the order of operations. I'm going to take the square root of both sides, and x is equal to 296.1 yards. Okay, so pretty basic. Both of these things aren't really that difficult. There are a few things mechanically that can get confusing with law of cosine, so be really careful with your order of operations. And other than that, it's just deciding what to use in which situation. So I'm going to post, if you want to know like a proof of why these laws actually work, I'll post a separate video of that. And there's a little quizzes for some practice, but hopefully this will help. This does come in handy in calculus sometimes, and it definitely pops up on ACTs in the last 10 problems a lot of the times, but they're actually super easy. So it looks intimidating. Hope this will help. And if we ever take the ACT, hopefully it'll help you guys out. Thanks. Have a good one.